Hey there, AP Stats kids. Today we're going to be looking at 7.1 about sampling distributions and such. Alright, so let's get right to the nitty gritty. So again, pause it, try the problem, and then go back. I'm using a new screen and recording's a little bit different, so hopefully this all works. Okay, so they took 250 simple RAM samples of size 20. They got their mean and standard deviation. And here's some questions we have about it. You might have to go back or screenshot the video and read the questions, or you can just go to this website. Actually, will give you the PDF. That's where I've stolen everything from, Mrs. Daniels AP Stats, and you can kind of print off and try it as well. And she has the solutions as well, so you can probably just do that if you want to save yourself some time. Thanks, Mrs. Daniels. So, is this a sampling distribution? Well, no. A sampling distribution has to contain every value possible from a SRS of size 20. What this is a simulation. Okay? So this is a simulation of a sampling distribution, but it's not a sampling distribution. B, describe the distribution. So when I describe this distribution, I'm going to use SOCOV, right? Sorry, this is going to be very verbal intensive. I'm trying to save myself a little bit of time and energy. So SOCOV. S, shape. So the shape would be symmetric, right? When you look at this, it is symmetric. It's outliers. There doesn't seem to be any outliers. C, center. The center is at 64. Mean 64. And variance, we don't know. The range is from 62.4 to 65.7, right? So again, whenever you're describing just a distribution, you're using SOCOV, right? Shape, outliers, center, variance. All right? All right, so suppose the height of the 20 girls in the class actual sample is 64.7. What would you conclude about the population mean height for 16-year-old females at school? Explain. Well, we would conclude that the population for the school... Hold on, I'm making boo-boos here. So they got 64.7, right? So I'm going to go up here and look at 64.7. SOCOV. And 64.7 is about right here. And we can look at that, and it looks like 4, 5, 6, 7, 8, 9, 10, whatever. It looks like about 10% of the time, I'm cheating, you get a value of 64.7 or more by random chance with a simple random sample if the mean was 64. So that tells me, what can you conclude? Remember, rule of thumb is that 5%. That means it's completely plausible that the population height of those females in that school is actually 64 inches, and it's just that that sample got 64.7. All right. Again, sorry, I'm not writing a lot. You might have to go back and listen again. Just trying to save us all a little bit of time. Choosing cards. We use Fathom. Who would have fathomed that we did it? To simulate 500 simple random samples of size 5 of deck of cards described on the previous page. The graph shows the distribution sample median for these 500 samples. So they took 500 samples with a computer machine. Now, is this the sampling distribution of the sample mean? No, because we did not use all possible samples of size 5. So it's not an exact sampling distribution. Okay? Describe it. Oh. Yep. Supposed to, and still do the one use activity. However, you took a simple sample 5 is 4. Does this show that the student's deck was different? So, you did it, and It was 4. Does this? No, it doesn't show that it's different because it got 4 or less by chance more than 5% of the time. Okay? Because it got more or 4 or less more than 5% of the time, it does not have convincing evidence. Now, if you would have done that and took a sample of 5 and you would have gotten 1 or 2, then you could say it's plausible. It's possible that it is different than what they actually said, because by chance it doesn't occur very likely. Okay. Okay, we're gonna go over this kind of more when we actually do the fun stuff. All right, so let's look at 7.2. The candy machine. You got a candy machine. You want some candy? John Candy Machine? It's a joke. You guys probably don't even know who John Candy is. He's a great actor. Look him up. It's a delight. Sorry, I have to open another file. I could have paused it. Oh, mama. All right. So we're looking at the candy machine. And you're reading, you're going to try it. You're going to take a simple random sample, 25 from the machine, and we're going to look at what's the mean and of the sampling distribution. Well, it's a proportion, right? This 15% is a proportion. Because it's a proportion, we are going to use our handy dandy formula for the mean of a sampling distribution of proportion, which, if you recall, it's square root of p times 1 minus p all over n, right? So for this one, my p is 0.15, because that's what we're saying success is. So we're going to do square root 0.15 times 1 minus 0.15 is 0.85 all over our sample size of 25. When I do that, I got 0.0714. Okay? Now remember, we can't actually do this unless the 10% rule is met. For this one, is 25 candies is less than 10% of all the candies in the very large candy machine. What do you guys think? Yeah, it's met. Because it's very likely there's probably more than 250 candies in the machine. Remember, we have to check that, because if there isn't that many candies in the machine, that means the samples won't be independent, right? Because every can you take out changes the probability that much. Because of that, we can find the standard deviation. All right. So our standard deviation. Guys, why'd you let me do this? This wasn't the mean. I found the standard deviation. I was looking at the wrong spot in my notes. I'm sorry. That's the formula for standard deviation. I found standard deviation, then I checked 10%. I'm so sorry. My mean is just n times p. I have 25 candies. Proportion is 0.15. And that means I got, for that one, I got 3.75. Which tells me I expect 3.75 orange candies in a simple random sample of 25. I'm so sorry. That's the mean. And this is the standard deviation of my proportion, right? All right. Ah, jeez. No bueno. No bueno. No bueno. Okay. Well, at least I figured that out now. Now, is the sampling proportion normal? Are any of us really that normal? Come on, man. Come on, candy machine. Let's figure it out. Well, to check normal, because it's a proportion, we are going to do the law of large counts, which means my n times p and my n times 1 minus p, right, should both be bigger than equal to 10. No, it does not count, because we know n times p is 3.75, so it does not. It is not normal. It fails. Okay, it fails law of large counts. But if you change the sample size to 75, now is it? Well, let's do our n times p, so 75 times 0.15, and our 75 times 0.85, right? Well, 75 times 0.15 is 11.25. And this one's definitely bigger. So yes, it would be normal now because it passed law of large counts. Alright guys, we're gonna keep trucking here. Planning for college. Y'all are gonna be in college soon. Maybe. Alright, so superintendent wants to know what to do for your college. You guys can read good. So what's probability? Oh, I guess I should. Okay. So, how many will be within 7 percentage points of the true value? Alright. Is this normally distributed? So is NP and n times 1 minus p both greater than or equal to 10? You can take my word for it is, because 0.8 times 125 is definitely bigger than 10. And then 0.2 times 125 is definitely bigger than 10. Okay? So, it's normal. Because I know this is normal, I can use Normalcdf to find a probability. Okay? So within 7 percentage points of the true value, right? So 7 percentage points of the true value, which would be, we know it's 8.8%, right? So I'm going to do Normalcdf. I'm going to do 7 below 80%, so 0.73. I'm going to do 7% above, so 0.87. I'm going to do a mean and a standard deviation. Oh no, what is the standard deviation, Mr. Twiller? Well, that's a good question. I'm happy you asked. Remember, I have to do square root of p, which is 0.8, times 1 minus p, which is 0.2, all over n, which was my sample size of 125. When I do that, I get the magic number of 0.036. That's my standard deviation. Plug that in my calculator, and I get 9.948. So about 95% of them fell within that range. The true value would. The super. He's a super. He has a super suit. Alright. Alright. Who owns a Harley? A Harley Quinn? Alright, so 14% of all motorcycles in the United States are Harley Davidsons. You plan interviewing in a simple random sample of 500 owners. How likely is it that your sample contains 20% or more? So I'm going to do the same thing. Is it normal? Is n times p and n times 1 minus p bigger than 10? Well, yeah, you're doing a sample size of 500, okay? 0.14 times 500 is bigger than 10. That's a 10. So it's normal. All right? So because this is normal, I can do Normalcdf again. So I'm going to do Normalcdf, 20% or more. So I'm going to go from 0.2 to 1 you could do, or 999999999. But I'm just going to put 1 because it makes sense in my brain. The mean is 0.14 of the proportion. I should say the true proportion is 0.14. Oh no, what's my standard deviation? Well, I have to go through and find it again. The square root of p, which is 0.14, times 1 minus p, which is 0.86, all over my n, which is 500. When I plug that in my calculator, I got 0.0155. So that's my standard deviation of the distribution. When I plug that in, I get 0.00057, which means it is extremely unlikely to get a sample to contain more than 20% of people who own Harleys in a sample of 500, which makes sense. 500 is quite a large sample size. All right, we're almost there, guys. Let's look at 7.3. Buy me some peanuts unless I'm allergic. At the Peanutty Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. Why do I do this every time at this point? It's like I go crazy at 15 minutes. Distribution is normal. Mean of 16.1 ounces. Standard deviation of 0.05 ounces, right? All right. What's the chances? You guys can read. All right. What A is asking, would it be more likely that you select one jar, would it be way less than 16 ounces, or 10 jars, and the average is less than 16 ounces? Now, if you're just grabbing one individual item, there's a lot of variation within when a sample size of 1, right? Because your standard deviation is going to be huge because you're dividing by 1 in the calculation. Just look at a room of people. How many people in that room are the same height? Right? But if I took samples of 10 people in that room, which they shouldn't be, they're quarantined, and took their average, you could get the same number multiple times. So, which one is more likely to have or to weigh less than 6 ounces? Will be the one jar. Because you're taking the average of 10 jars, it's going to be closer to the actual mean. So find the probability of each event described above. All right, let's do it. Let's see if we were right. So a single jar, what's the probability that a single jar weighs less than 16 ounces? So it's a normal CDF. All right, and we're doing mean now. So my mean of mean is mean, right? The standard deviation is going to be your you take your what should I say? Your standard deviation, you take it and you divide it by square root of n to get your distribution standard deviation. Thank you. So if we're just grabbing one jar, normal CDF, from 0 to 16, you could use negative 999 there too. We know the mean to be 16.1. And the standard deviation, because it's just 1, is, well, 0.15. I plug that in, I get 0.25. So there's a 25.25% chance of grabbing one jar that's less than 16 ounces. But now what about the 10 jars? The 10 jars. So this one, everything else is the same. You're doing normal CDF from 0 to 16. The mean is still 16.1 because that hasn't changed. But now standard deviation, I have to do 0.15 divided by square root of n. Because the bigger the sample, the smaller your standard deviation of the sample. When I plug that in, I get 0.0175. So that's much lower probability that if you select 10 jars, the mean is less than 16. All right, as the Muppets once said, we're going to keep moving right along. Mean text. Don't be a mean texter. Some people think I'm very short and abrasive in text. I'm not a great texter. You should call people if I have something to talk about. All right. So again, we're looking at means of distributions, not proportions this time. Suppose that number of text sent during a typical day by a random person is that, how likely is it that 50 random students will have sent more than 1,000 texts in the last 24 hours? All right. So first thing I need to ask myself is, are conditions met? Is it independent? Okay, so does 10% pass? Is 50 students less than 10% of a large high school's population? Yes. Is it normal? Yes. The sample size of 50 is greater than 30, right? Okay. Is it a random sample? Yes. All right, so we can calculate this. And we also know it's normal because of the central limit theorem, CLT. I think I might have videos on it. I don't know if I do. So I get to do normal CDF. So I'm going to do normal CDF. So we want to set 20 sample of 50 with a mean. Okay, so we need to find the average per student. So the average text per student, if I do 1,000 divided by 50, they're looking for an average of 20. So we're going to go from 20 to 99999 because it could be 20 or more. The mean is 15. We got that from right here. Now the standard deviation, because we're taking sample, we do 335 divided by square root of 50. Right? And when I plug that in my calculator, I get 0.1562. So there's a 16% chance that a random sample of 50 high school students will send more than 1,000 texts in a day. All right? We're almost there, y'all. All right. Bad carpet. Bad carpet. No carpet. No. All right. You guys can read it. Pause if you need to. Check conditions as you go. Is it a simple RAM sample? It doesn't say so. I don't know. Is it normal? Or, yeah, is it normal? Yeah, because don't even, whatever, it doesn't matter. The population doesn't have to be normal for the sample to be normal, because 200 is bigger than 30, central limit theorem. Is it independent? Does 10% pass? Yeah, it does, because there's so many carpet squares. So many. All right, we can get right to it then. So, I'm going to do normal CDF, of course. I'm going to go right to the mean and standard deviation. My mean's going to be 1.6. Standard deviation is going to be 1.2 divided by square root of 200, right? And I'm looking for 2 or more. So from 2 to 99999. When I plug that in, I get 0.0000001. So there's basically no chance of finding more than 2 errors. Thanks, guys. I went a little bit quicker today. I'm sorry. Not sorry. You're probably bored. Have a great day.